Okay, so this is going to be our last video from this unit, and we're going to finish up talking about standing waves and then look at some examples to get ready for our upcoming test. Okay, so in the last video we talked about two types of standing waves. Standing waves on a string, where the boundary condition is that the two endpoints are nodes. And then we talked about the first type of standing wave that you see in pipes, which is where one end is open and one end is closed. And that means the boundary condition for that situation is the open end is an antinode, because that's where the air molecules can move the most, and the closed end is a node because the air molecules can't move on that side. And that type of setup has an interesting feature where you only get the odd harmonics, and that's just kind of how the math works out. And so we're going to do a quick example with that, and then talk about the last type of standing wave, which is a pipe open at both ends, and then we'll look at some IB examples. Okay, so let's take a look at this example right here. So the question says the speed of sound waves in air is 340 meters per second. Determine the fundamental frequency of a closed end air column that has a length of 67.5 centimeters. Then use your answer to determine the frequency of the next highest harmonic. Okay, so there's a lot going on in this question, so let's start with a picture. As far as the equations for standing waves goes, I would highly recommend that you just understand the concepts and understand how to do these derivations on your own rather than memorizing equations. And so the concept here is we have a pipe open at one end and closed at the other. And so we know that the boundary condition is that you have to have a node at the closed end and an antinode at the open end. And that's for any harmonic you want. Now, when it's talking about the fundamental frequency, it's talking about the first harmonic. And what the first harmonic looks like for this type of pipe is it looks something like this. And we talked about this in the last video. And even though it's hard to see because I drew it kind of badly, if you stare at this long enough, you should be able to see that if the length of the pipe is L, then this is actually a quarter of a wavelength. You can imagine a full wavelength has one full up part and one full down part. And this is kind of like half of an up part. Okay, so half of a half is a quarter. Okay, so if we have L equals lambda over 4, that means the wavelength is equal to 4 times L. And then we can use the wave equation to find the frequency for that first harmonic. Okay, so F equals V over lambda. So we get V divided by 4L, and then we just need to plug the values in. Okay, so F1, this is F1, that would be equal to the speed of the waves, which is 340 meters per second, divided by 4 times L. Do pay attention to the units. Okay, so this is in centimeters, so let's convert that, because this is 340 meters per second. Although I guess if we wanted to, we could also convert the meters per second to centimeters per second, and either way you'd get the same thing. Okay, but to convert this from centimeters to meters, you just divide by 100. So this is going to be divided by 4 times 0.675. And I'm going to put that into my calculator. 340 divided by 4 times 0.675. And I get about 126 hertz. I'm rounding up, it's actually 125.9. I'm just going to round that up. Now, the question then goes on to say, then use your answer to determine the frequency of the next highest harmonic. Okay, so this is one of those where either you could draw the picture. You could be like, okay, well, it has the same boundary conditions. I still have to have, antinode on the open end, node on the closed end. I'm basically just adding an extra node. Okay, and I know that they have to alternate back and forth. So, if I have a node here, I would have to have an antinode, and then another node, and then an antinode. And so the picture would look something like this. Again, I apologize for the bad drawing. And if you squint really, really hard at my squiggles, you can see that that is, half a wavelength right there, and then another quarter. And so this is 3/4 of a wavelength. Or I suppose you could just happen to remember that this type of pipe only has the odd numbered harmonics, and so the next one after the first harmonic would be the third harmonic, and so you could just say, you know, by definition, F3 equals 3 times F1, which is 3 times 126, which would be 478 hertz. Okay, so whatever works for you. Again, it's always better to just understand the concepts and understand how to draw the picture and get the equation from that, rather than memorize the equations. Okay, so pause there if you need to look at that some more. Okay. Okay, so let's take a look at one more. It says a pipe open at both ends has a length L. The speed of... Okay, well actually this is a pipe open at both ends. Let's come back to this question actually. Let's talk about a pipe open at both ends. Okay, so basically this is the last type of standing wave we're going to see. A pipe open at both ends means you have a boundary condition whereby each end has to have an antinode, because if the end is open, that means the air can vibrate at a maximum there. And so what you just saw there, I apologize for the noise, but what you see right here is the first harmonic for a pipe open at both ends. Okay, so notice we've met the boundary condition. We have antinodes at the endpoints, but we have to alternate between node and antinode, and so that's why we have a node right here in the middle. And so this is the first harmonic for this type of pipe. Okay, now in this case it's kind of difficult to see exactly how much of a wavelength this is because of the way it's drawn, but this is actually, believe it or not, the length of the pipe is L. This is actually half of a wavelength. Okay, so normally we think of a full wavelength that has like an up part and a down part, but basically what we have here is we actually have half of an up part and then half of a down part. And so if you put, you know, two quarters together, you get a half. And so even though it looks kind of funky, this is actually half of a wavelength. Okay, and so interestingly enough, you get lambda equals 2 times L, and if you go through the math using the wave equation and whatnot, you get an equation for the first harmonic for this type of pipe that looks like V over 2L, which is actually the exact same, that's a 2 and that's an L, which is actually the exact same equation for the first harmonic for the wave on the string, which has the exact opposite boundary conditions. Because for a string, the boundary condition is that the endpoints are nodes, and you have an antinode in the middle. This is kind of the opposite of that, because here you have antinodes at the ends and a node in the middle, but the equation works out to be the same, mathematically speaking. Okay, so just to show you what some of the other harmonics look like, let's see if we can click through here. This would be the next highest harmonic, where basically we've just added another node, and so we have antinode, node, antinode, node, antinode. Okay, and there, again, it's kind of really difficult to see, but here the length is equal to 1 wavelength. And the reason is because we basically have a quarter here, and then we have a half wavelength, and then we have another quarter over here. So that adds up to full wavelength. Okay, and then this would be the third harmonic. So you do get all the harmonics with this when the equations actually come out looking really similar to a standing wave on a string. Okay, this is 3V over 2L. Okay, and so you are required to be able to make sketches of standing waves for any given harmonic. Practically speaking, they don't usually ask you about anything higher than the 5th harmonic. Usually it's more like the 2nd or the 3rd, but you are expected to be able to draw and interpret these sketches and then use the sketches to derive the equations for those frequencies and wavelengths. Okay, so that is something that you are expected to do. So with that being said, I want to go back to an example that we had before. Okay, so here we have a pipe open at both ends, has a length L. The speed of sound in the air in the pipe is V. The frequency of vibration of the first harmonic standing wave that can be set up in the pipe is blank. Okay, so remember that the equations are not given to you in the data booklet. So either you just have to remember this one, or you have to be able to derive it. Now, to be perfectly honest, I don't memorize any of these equations. I always start from scratch. So pipe open at both ends. I know at least the boundary condition, because that's just a concept thing. The boundary condition is you have antinodes at the end. The concept is because why do you have antinodes at the end? Because if the ends are open, the air can move at the ends. Okay, and if you have antinode and antinode, you have to have a node in the middle. So if you just understand the basic concepts of boundary conditions, you can get the picture drawn. Wow, that was a horribly drawn picture because it should have gone through the node there. But from this picture, even though my picture is really bad, I can kind of work out that this is half of a wavelength for reasons I discussed on the last slide, and so lambda would be 2L, and then I can always go back to my wave equation and find an equation for F. Okay, so F would be V over lambda, which would be V over 2L, and so the equation, or the answer to the question would be this. Okay, so that is a former IB question. That's a relatively easy IB question, of course. And again, I mean, I would recommend you understand concepts and just know how to derive these equations. If you wanted to, I guess you could just sit down and memorize all of them, but that seems more difficult to me. If you just happen to remember that's the correct equation, good for you. Okay, so pause there if you need to look at it some more. Okay, so I do want to do a few more examples. Okay, this picture right here is just showing you the standing waves in pipes. On the left side, you can see the standing waves in a pipe, open at one end and close at the other. How those harmonics look. Okay, these are the first three harmonics, or I guess I should say that the first, the third, and the fifth. And then over here we have the standing waves in pipes that are open at both ends. Okay, and so you can see how those look different as well. And remember, for pipe closed at one end and open at the other end, you don't have any even harmonics. Now, somebody always asks the good question, by the way, could you have a pipe that is closed at both ends? And the answer is yes, you could have a pipe that is closed at both ends, but practically speaking, if the pipe is closed at both ends, you can't really get air into the pipe, and so it would be difficult to produce a standing wave like that. And so theoretically, I guess you could, and then it would basically be the exact same situation as a wave on a string, because the boundary conditions would be the same. But I've never seen that on a problem, because again, how would you get air into the pipe to begin with? Okay, so let's just do a few more quick examples. Actually, I think we did this one already. So take a look at this question. Two pipes P and Q are of the same length. Pipe P is closed at one end, and pipe Q is open at both ends. The first harmonic of the closed pipe P is 220 Hz. The best estimate for the fundamental frequency of the open pipe Q is blank. Okay, so let's start with what we know. All right, I have two pipes. Pipe P is closed at one end. And I know that the first harmonic is going to look something like this. So this is pipe P. It has a length, let's call it L. And then pipe Q is the exact same length, so the length is L. But because it has a different boundary condition, the first harmonic picture is going to look a little bit different. This is Q. It's going to look something like this. For pipe P, I know that this is a quarter of a wavelength. So L equals lambda over 4. And I'm going to skip the messy algebra basically just to get F1 is equal to V divided by 4L. And I could also go back and use a wave equation for this one and show that F1 for this one should be V divided by 2L. Okay, we've done examples like that before. I'm not going to go through all that steps, but it's not difficult to show using the wave equation. Okay, so compare these two equations, because what they give us is they actually give us F1 for pipe P. Okay, they tell us that the first harmonic for pipe P is 220. So compare this F1 to this F1. What's the difference? Well, they're almost the same, except the F1 for pipe P is half of F1 for pipe Q, because there's a 4 here, there's a 2 here. So in other words, the this frequency over here should be half of this first harmonic frequency over here. But we know that this one is 220. Okay, so that means 220 is half of the first harmonic for pipe Q, and so that means the answer is B. Okay, because in other words, if I were to plug in numbers here, I know 220 equals V over 4L. And if you were to compare that to a different F1 where you had V over 2L, this one, the only difference between these two is this one is divided by 2, or this one is divided by 4, this one is divided by 2, so this one is half of this one. Okay, so the answer there is B. So pause it there if you need to look at that some more. Okay. And this basically just kind of has the breakdown of how that works. Okay. So again, pause it there if you need to look at that. And just to show you a couple more things. So we've been talking about standing waves on strings and pipes, but you can actually have two-dimensional standing waves. And so this is a drum head that has been attached to a machine that makes it vibrate at different frequencies, and it has black sand on it. Okay, and so you can actually get two-dimensional standing waves. You can see the different patterns here. So the first question says, the places where the sand is, does that reveal nodes or does it reveal antinodes? The place where you actually see the sand. It actually reveals nodes, because if you see sand on that part of the drum, that means the drum is not vibrating at that location. Okay? Whereas if it is vibrating, it knocks the sand off. Okay, so the sand actually reveals where the antinodes are. So two-dimensional standing waves are much more complicated to deal with than one-dimensional standing waves, but I don't know that you're going to see any problems with that per se. But it is an interesting concept to extend that to 2 dimensions. Why does the edge have to be a node? Because of boundary conditions. The edge of a drum is like tied down. That's how a drum head works. And so the drum head cannot vibrate at the edge, therefore you have the boundary condition that you have to have the edge be a node. And if you ever study physics or engineering at a higher level, then you actually do learn how the mathematics behind all of that works. It is an interesting thing, and again, it all comes down to understanding the boundary conditions. Okay, so I just am going to link this video so you can see kind of that demonstration from the last slide in a different way. Again, two-dimensional standing waves are kind of interesting to see. What you're going to see in this video is basically a 2D standing wave established on a plate that is forced to oscillate, to vibrate at different frequencies. And at different frequencies, you get different types of standing waves. It's much more complicated in 2 dimensions because you get different possibilities. And again, the plates where the sand ends up, those represent the nodes in the standing wave because the sand can't move if it's on a node. Okay, so I want you to check that out. I hope that you enjoy that video. As always, please let me know if you have any questions about anything, but we are now done with this unit. We're done with 4.4 and 4.5, and so you should be ready for your test. Okay, make sure you do all the problems that are in the textbook, especially over 4.4 where there's lots of different types of calculations. All right, let me know if you have any questions. and I'll see you guys in the next video.